Foundational integration work teaches the architect to track first cost and coordinate consultants. Advanced integration is what happens when the owner asks whether the design is really worth more than the cheaper alternative, and the only answer that works is a quantitative one. Life cycle cost analysis. Function analysis through fast diagrams. Structural architectural integration math. Performance specification logic. Peer review that actually catches things. Most architects bluff their way through these on exam day, and the exam knows it. Misread any of them and it will cost you the question, and on a real project, misread it and the firm gets sued by an owner who wanted the cheaper option defended. Here are 4 reasons the advanced layer carries the weight the PPD exam gives it. 4 reasons the advanced layer carries this much weight. First, life cycle cost analysis, LCCA, is the only tool that wins a first cost argument with a developer. You present value the operating cost over the service life, you compare alternatives on equal terms, and the more expensive upfront option often wins on net. The exam tests the actual math: discount rate, present value, study period, not the marketing pitch. Second, fast diagrams force value engineering to ask what function each component performs, and whether there is a cheaper alternative that performs the same function. Done right, fast protects design intent. Done wrong, value engineering is just budget triage. Third, structural architectural integration is the math of trade-offs. Shallower beams free up ceiling plenum but add steel weight. Longer spans reduce columns but deepen the structure. Concrete versus steel changes both. The exam writes prompts where one option clears the ceiling and another fits the budget, and you have to read the constraint. And fourth, performance specifications shift the design responsibility to the contractor. And peer review is the design team's last chance to catch what an internal review will not. The exam tests when both belong in the project. Here are the 5 advanced subsections in the order the module walks them. Walking the 5 tools. 4.1 is life cycle cost analysis, present valuing every cash flow over the service life of the alternative under a defined discount rate, so the developer sees first cost and operating cost on the same axis. 4.2 is fast diagrams, function analysis system technique, the structured method that asks what each component does and what cheaper alternative would do the same job. 4.3 is structural architectural integration, the trade-offs between span, depth, column spacing, ceiling plenum, and structural material. 4.4 is performance specifications, telling the contractor what the system must do rather than how to build it, and the moments where that shift in responsibility is appropriate. And 4.5 is the peer review and design review process. Who reviews, at what milestone, against what criteria, and what gets documented. One posture shift before we step into section 4.1. 4 things to hold in mind. First, advanced cost questions are quantitative, not narrative. Your job is to find the tool that produces a comparable number, lifecycle cost, function value, span versus depth trade, and apply it. Intuition will not get you to the right answer on these prompts. Second, an LCCA only wins the argument when the discount rate, the study period, and the scope of cash flows are stated explicitly. The exam tests whether you stated them. Third, fast and value engineering exist to protect design intent, not to gut it. When an exam prompt gives you a VE proposal, the right answer is almost always the one that preserves function rather than the one that just saves the most money. And fourth, peer review and design review are scheduled events with criteria attached, not informal walkthroughs. The exam tests the timing in the project schedule and the scope of what the reviewer is checking. With that posture set, we step into section 4.1. Most architects walk into a value engineering meeting having argued only first cost, and the contractor wins every time. The cheapest curtain wall, the cheapest HVAC system, the cheapest roof. Those numbers are easy to defend in a single PDF. and you will recommend them by default if nothing else is on the table. Lifecycle cost analysis exists because that default is wrong about 10% of the time and disastrously wrong the other 90%. A high-performance system that costs roughly $280,000 more at construction can save $440,000 over 30 years of operating bills. But only the architect who built the LCCA wins that argument. The architect who skipped it watches the owner pick the cheaper option and absorb the operating surprise 3 years later. And when the owner gets sued over comfort claims and the redesign cost falls on the architect personally, the lawsuit traces back to that missing LCCA, and the architect's deposition is short. 6 cost categories drive every honest lifecycle comparison. Leave one out, and the analysis collapses. 6 categories, and every one of them can flip the comparison. Initial cost is the only one most architects can quote without doing math. It is the construction outlay plus design fees. Operating cost is the steady drumbeat of utility bills, water, and staffing across the building's useful life, and it is where high-performance systems earn back their premium. Maintenance cost is the cleaning, sealant replacement, gasket swap, and warranty service that no spec sheet headlines but every facility manager tracks. Replacement cost is the major component refresh, a recladding at year 30, a chiller overhaul at year 15, that has to be priced in present value dollars. Residual value is what the asset is still worth at the end of the analysis period, and it usually flatters durable assemblies. Disposal cost is the end-of-life expense, including hazardous material handling, that owners frequently forget until the wrecking ball is on site. Drop any one of these, and the LCCA reads more like a sales pitch than an analysis. Apply those 6 categories to a real HVAC decision and watch which system actually wins. Same 50,000 square foot office, 2 HVAC options, 30-year horizon. Standard rooftop units land at $400,000 in first cost and roughly $62,000 a year in operating cost, which compounds to about $2.26 million over 30 years. The high-efficiency variable refrigerant flow system costs $680,000 to install, $280,000 more, exactly the number an owner zeroes in on. But its operating cost drops to $38,000 a year, and over 30 years the cumulative total is $1.82 million. The expensive system saves $440,000. This example is undiscounted for illustration. A proper LCCA per ASTME 917 discounts each year to present value using a real discount rate, typically around 3 to 5%, and the high-efficiency system usually still wins, but by less. The architect who presents only first cost loses to the contractor saying, "Go with the cheaper one." The architect who presents the LCCA wins the client's confidence and frequently wins the project. Even a clean LCCA has 4 ways to mislead the owner. Know them before you present. 4 ways an LCCA can mislead even when the math is technically right. Discount rate sensitivity is the biggest. A higher discount rate makes future savings look smaller and favors the cheap first cost, while a lower rate makes long-term savings look generous and favors the premium system. Document the rate you assumed and run a sensitivity check at plus and minus 2 points before you present, because changing from 3 to 7% can flip the winner. Omitted categories is the second pitfall. Leaving out maintenance or replacement to keep the table simple biases the result toward whatever has low first cost, because cheap systems usually need more upkeep. Mismatched analysis periods is the third. Comparing a 15-year roof to a 30-year roof without normalizing the comparison is comparing 2 different bets, and you have to either extend the short-lived option through a replacement cycle or shorten the long-lived option's horizon. Ignored escalation is the fourth. Energy prices, labor, and replacement parts rarely hold flat for 30 years, and most legitimate LCCA templates apply an annual escalation factor specific to each cost line. 5 takeaways anchor the way you should walk into the next LCCA conversation. 5 things to anchor before you author another life cycle analysis. Lowest first cost does not equal lowest total cost. That is the single most tested distinction in the entire cost analysis section, and the architect who internalizes it controls the value engineering conversation. Every legitimate LCCA includes all 6 categories: initial, operating, maintenance, replacement, residual, and disposal. And any analysis that skips one is suspect. Present value comparisons per ASTME 917, not raw, undiscounted sums, are the exam-correct method. Discount rate is an assumption that has to be documented and stress-tested with a sensitivity check, because moving it a few points can flip which option looks like the right answer. And finally, the architect who walks into the conversation with the LCCA in hand controls the discussion. The architect who only quotes first cost loses to the contractor every time. Most architects who pitch sustainable upgrades to skeptical owners lean on simple payback because the math fits on a napkin. And every time they do that, the owner asks a follow-up question they cannot answer, and the upgrade dies. You need a sharper toolkit. Total cost of ownership extends LCCA to include indirect costs, productivity, user satisfaction, environmental externalities, that change which option actually wins. Return on investment math, properly done, makes the case for the higher first cost. Done sloppily, it makes the architect look like an advocate rather than an analyst, and the owner's CFO politely overrides the recommendation. The risk is real. An architect who recommended a costly, sustainable system on simple payback alone has been sued for negligent professional advice when the projected savings did not materialize. 4 metrics show up in every real ROI conversation. Know which one answers which question. 4 ROI metrics, each one answering a different question. Simple, payback is added cost divided by annual savings, and it gives you a quick screening number, 8 years, 12 years, that tells you whether to keep investigating. It is not a decision tool because it ignores the time value of money and ignores what happens after payback. Net present value is the decision tool. It sums the discounted future cash flows and subtracts the initial cost, and the option with the higher NPV wins on the math. Internal rate of return is the discount rate at which NPV equals 0, and you use it when the owner has a specified hurdle rate the investment must beat. Savings to investment ratio is the present value of savings divided by the present value of investment cost, and a ratio above 1.0 means the upgrade pays for itself across the analysis period. Use the wrong metric, and you can be technically correct and operationally wrong. A fast, simple payback on a short-lived system loses to a slow, simple payback on a long-lived system every time. Typical paybacks for common sustainable features fall into ranges you should be able to quote, with hedging. 5 typical ranges to anchor your intuition, all framed as illustrations rather than guarantees, because local utility rates and incentives swing them. High-efficiency HVAC systems typically pay back in roughly 3 to 7 years from energy savings alone, which makes them the easy yes on most upgrade conversations. Daylighting with automated controls runs around 5 to 10 years, and the productivity gain literature on top of the energy savings can shorten the case further if the owner buys those numbers. Green roofs are slower, 15 to 20 years on energy alone, but stormwater management credits in many jurisdictions cut that materially when the building would otherwise face detention requirements. Solar photovoltaic is roughly 7 to 12 years right now, with the range driven by local electricity rates, net metering rules, and federal or state tax incentives. Low-flow plumbing fixtures pay back in roughly 1 to 3 years and are almost never the wrong call. These are illustrative ranges. Every real project needs site-specific numbers before you stake your professional advice on them. The risk isn't the math. It's confusing simple payback with NPV, which the exam tests directly. Here is the trap the exam loves and the conversation owners get wrong. A compressor with a 5-year simple payback and a 7-year service life looks attractive on the napkin, fast money back. But the owner only gets 2 years of free savings after payback. And when the compressor fails at year 7, the cycle restarts. A roof with a 10-year simple payback and a 30-year service life looks slow on the same napkin, twice as long to break even. But the owner enjoys 20 years of free savings after payback. And on net present value, the roof wins comfortably. The architect who recommends on payback alone can be technically defensible and still get sued when the owner's expected savings did not materialize because the system reached end of life before the savings curve really kicked in. The exam rule is plain. Simple payback is for screening. NPV, or savings to investment ratio, is for the actual decision. 5 takeaways close the loop on how to talk about ROI without overpromising. 5 takeaways from the ROI framework. Total cost of ownership extends lifecycle thinking to indirect costs, productivity, user satisfaction, environmental externalities that frequently determine which option actually wins on the owner's spreadsheet. 4 metrics serve 4 different purposes: simple payback for screening, net present value for the decision, internal rate of return when there is a hurdle rate, and savings to investment ratio for ranking multiple upgrades. Simple payback is a screening tool that ignores both the time value of money and what happens after payback, so it does not belong in the recommendation slide of a real value engineering presentation. Service life matters as much as payback speed. A long-lived system with slow payback beats a short-lived system with fast payback on net present value every time. And finally, hedge your illustrative paybacks. Utility rates and incentives change too fast for typical figures to read as commitments without that hedge. Most architects who get blindsided by an over-budget estimate make the same first mistake. They treat the conversation as a math problem instead of a contract problem. Under AIAB 101, if the lowest bona fide bid exceeds the owner's budget, you redesign at your own cost unless the overage traces directly to scope changes the owner directed in writing. That is a clause architects sleepwalk past at contract signing and then live to regret. You will be personally liable for the redesign hours if you cannot document the chain of decisions that drove the cost. Lawsuits and fee disputes between owners and architects over redesign cost are one of the most common categories of professional liability claims in this division. The reconciliation conversation is also where the relationship with the owner is either preserved or fractured. 6 steps walk you through the conversation in the order it has to happen. 6 steps, and the order matters. First, verify the estimate. Every architect who has been around the block has seen a quantity takeoff that double-counted a major system or applied a regional cost multiplier that was off by a third. Before you redesign anything, audit the assumptions behind the number. Second, identify the gap. Not just how many dollars over, but in which building systems, because the redesign strategy depends on whether the structure is over by 10% or the curtain wall is over by 50%. Third, evaluate value engineering options that preserve function. The VE menu must come from the design team first, because letting the contractor drive that conversation cedes both control and quality. Fourth, prioritize with the owner. Let the owner choose which VE items to accept, because those choices have program and quality consequences that are not yours to make alone. Fifth, adjust scope if the VE menu does not close the gap. Deferred construction, phasing, or program reductions are tools the owner has and you do not. And sixth, document everything in writing. Verbal agreements during a tense reconciliation will not protect anyone when the lawsuit lands. B101 spells out exactly who carries the redesign cost, and the answer is rarely the owner. 5 B101 provisions that govern every budget conversation. The architect designs to the owner's budget. That single phrase makes the budget a binding design constraint, not an aspirational target you can drift past. If the lowest responsible bid exceeds the budget, the architect revises the documents at no additional cost, unless the overage was caused by scope changes the owner directed in writing. The owner has the option to increase the budget, but is not obligated to do so, and most owners will exercise that option only when there is no realistic redesign path that holds the program. The owner may reduce scope to bring the project in line, deferring a wing, eliminating a feature, or pulling tenant improvements out of the base contract are all owner decisions you cannot make unilaterally. And the owner may authorize rebidding when market conditions look more favorable, although that route adds schedule risk. Internalize these 5, and you walk into the reconciliation meeting knowing which obligations are yours and which belong to the owner. 4 conversations with the owner determine whether the reconciliation goes well or badly. 4 conversations the architect has to lead with the owner, ideally before the reconciliation meeting hits a fever pitch. First, was the budget realistic for the program at the very start? Or is the team now reconciling an unrealistic baseline that was set before the design was developed enough to challenge it? If the baseline was unrealistic, that conversation belongs at the front of the meeting, not at the end. Second, were there owner-directed scope changes during design that drove the overage? And are those changes documented with written authorizations from the owner? If they are, the redesign cost burden under B101 shifts and the meeting changes character. Third, does the owner prefer VE first, program reduction first, or budget increase first? Owners have strong preferences here, and the architect needs to know them before recommending a path. Fourth, what is the owner's appetite for rebidding versus accepting a negotiated bid with VE adjustments? Each path has schedule and quality implications, and the owner is the only one who can choose. 5 takeaways tighten the way you handle the next over-budget conversation. 5 takeaways from the reconciliation playbook. B101 makes the budget a binding design constraint and shifts the cost of post-bid redesign onto the architect unless owner-directed scope change is the documented cause. 6 steps run the conversation in order. Verify the estimate, identify the gap, evaluate value engineering options, prioritize with the owner, adjust scope if needed, and document every decision. And skipping any of them invites trouble. The owner alone chooses among VE acceptance, scope reduction, budget increase, and rebidding, because each path involves trade-offs that are not the architect's to make unilaterally. Owner-directed scope changes must be documented in writing at the moment they happen, because reconstructing them after the over-budget bid lands is when the deposition starts. And finally, document every decision and rationale in writing. Verbal agreements collapse under the pressure of a fee dispute or a lawsuit, and the architect who relied on verbal approvals will lose. Walk into a value engineering session without a function analysis, and the conversation collapses into a list of items somebody wants to cheapen. Most architects who get sued over VE decisions made that mistake. They accepted a cost cut without verifying that the function survived. FAST stands for Function Analysis System Technique, and it forces the team to map what each building component actually does before anyone proposes a substitute. You read a FAST diagram left to right to answer how, and right to left to answer why. And that simple navigation prevents the most expensive mistake in value engineering: solutioneering. Solutioneering is jumping to a cheaper alternative before you understand the function it has to perform. The architect who lets that happen owns the lawsuit when the cheaper alternative does not perform. 5 FAST concepts run every diagram. Learn them in order, and the rest of the technique falls into place. 5 concepts populate every FAST diagram. Higher order function is the why, the purpose being served, and in a building enclosure analysis, the higher order function is to protect occupants. Basic function is the primary function being analyzed, such as enclosed space in that same example, and it is what the VE study is targeting. Required secondary functions support the basic function. They include resist weather, control heat flow, manage moisture, and accommodate movement, and they cannot be cut without compromising the basic function above them. Design objectives are desired but not essential. Examples are enhance aesthetics, minimize maintenance, and simplify installation, and these are the legitimate VE targets when first cost has to come down. And the how-why logic, reading left to right to answer how a function is achieved and right to left to answer why a function exists, is the navigation that keeps the team honest. Get the categories wrong and you cut a required secondary function while thinking you cut a design objective, and the lawsuit follows. 6 steps build a FAST diagram, and the order is non-negotiable. 6 steps build a working FAST diagram, and you do not skip them. First, define the scope of the study. Is the team analyzing the curtain wall, the structural frame, or the entire envelope? Without a scope statement, the team will drift across systems and produce no actionable output. Second, identify every function using verb-noun pairs. Enclose space, support load, resist weather, control heat flow, accommodate movement. And that grammatical discipline forces a function-first lens rather than a product-first lens. Third, classify each function as basic, required secondary, or design objective before anyone prices it, because classification determines which functions are protected and which are VE targets. Fourth, arrange the functions in how-why logic chains reading left to right, left for how, right for why. So each function has a stated purpose anchored above it. Fifth, identify the highest cost functions on the diagram, because those are the VE targets where alternatives produce the biggest savings. And sixth, brainstorm alternatives that achieve each high-cost function at lower cost while preserving every required secondary function and design objective above it. 4 classic VE targets emerge from honest, fast work, and 4 traps that look like VE targets but aren't. 4 VE target classes that honest, fast work surfaces. Over-specified design objectives, such as an aesthetic upgrade that costs disproportionately more than the function it serves, show up in the right side margin of the diagram and are the easiest legitimate VE targets. Duplicate functions are surprisingly common, 2 building systems performing essentially the same job because nobody traced the function chain end to end, and consolidating them frees significant cost. Premium products applied to basic functions are a third pattern, where a boutique manufacturer was chosen for an enclosure function that a commodity supplier handles at half the price, and FAST forces that comparison into the open. And unstated functions the design quietly assumes, such as fire egress provisions, daylight access, or acoustic separation, get caught when the diagram exposes the gap, and you fix them in VE rather than discovering the omission in construction administration. Skip FAST, and these stay invisible until a contractor's RFI lands, or worse, a building official's correction notice. 4 takeaways anchor how you use FAST in the VE room. 4 takeaways from the FAST framework that you can carry into the next value engineering session. FAST forces you to map function before form. Reading left answers how a function is achieved, and reading right answers why the function exists. 5 concepts run every diagram: higher order function above, basic function in focus, required secondary functions supporting it, design objectives as the legitimate trim layer, and how-why logic as the navigation. 6 steps run in strict order: define scope, identify functions using verb-noun pairs, classify each one before pricing, arrange them in how-why chains, identify the highest cost functions, and brainstorm alternatives. And skipping any step produces a sloppy diagram that misleads rather than clarifies. The single most expensive trap is solutioneering, jumping to a cheaper alternative before understanding the function it must perform. And that trap is exactly what FAST exists to prevent. Required secondary functions are protected. Design objectives are the legitimate VE targets when first cost has to come down. Every architect who has watched a design bid build project come in 20% over budget has had the same thought. If only a contractor had told us about the cost problem 6 months ago. That thought is the architecture of regret, and you avoid it by understanding how the delivery method governs when VE can actually happen. Under design bid build, the contractor arrives after design is complete, and any post-bid VE becomes a contractor change order rather than collaborative design improvement. Under CMAR, the construction manager is on board through design and provides continuous cost feedback. Under design build, the builder shapes design from day one. And under IPD, every team member shares in savings. Pick the wrong method, and you can be sued for negligence when post-bid VE produces a result the owner could have had earlier and cheaper. 4 delivery methods each create different VE windows. Know which one you have. 4 delivery methods, 4 distinct VE windows. Design bid build is the most common and the most constrained. VE happens during design only because once the project goes out to bid, any contractor proposed change is technically a change order and runs through formal channels with profit markups. The formal VE study during SD or DD is your one real shot. CMAR opens the window much wider. The construction manager is engaged through design and provides continuous real-time cost feedback as alternatives surface, which makes it the most effective VE method in practice. Design build folds VE inside the design build team itself. The builder shapes design for constructability and cost, and the architect is one voice on a multidisciplinary team rather than the lead. Integrated project delivery, when used, creates the strongest VE motivation because every party shares in the savings, which means the contractor actively hunts for cost improvements that protect the owner's program. Pick the wrong method for the project type, and the VE opportunities you wanted simply aren't available. When VE happens during construction, it lands as a VECP, and VECPs come with their own rules. 6 rules govern value engineering change proposals. The post-bid mechanism for VE during construction. First, VECPs occur during construction, and the contractor is the one who proposes the alternative. The architect cannot initiate one. Second, savings are typically shared between owner and contractor, often on something close to a 50-50 basis, which is why contractors are motivated to find them. Third, the architect reviews every VECP for design intent, code compliance, and performance, not just cost, and a sloppy review here is where lawsuits start. Fourth, a VECP cannot reduce the functional requirements of the contract. If the contractor's proposal would degrade function, the architect must reject it, regardless of the savings. Fifth, federal projects often require VECP provisions in their contracts as a matter of policy, so the conversation is not optional on those jobs. And sixth, VECPs show up most in design bid build and CMAR deliveries. Under design build and IPD, the savings get routed through the team contract rather than as a discrete VECP. Architects routinely confuse VECPs with substitutions. They are not the same, and confusing them causes claims. Architects routinely confuse VECPs with substitutions, and the confusion is professional negligence waiting for a deposition. A VECP changes the design approach while maintaining function. Different system, different method, sometimes different sequence, and it requires owner approval plus a shared savings agreement. The architect reviews it against design intent, code compliance, and performance. A substitution, by contrast, replaces a specified product with an equivalent alternative. Same approach, same method, different manufacturer or model. And the review criterion is product equivalence against the specification. Substitutions live under the substitution clause in the bidding documents and are processed by the architect under that clause's rules. VECPs are more common in federal and public sector contracts where statute often requires the mechanism. Substitutions are more common in private commercial contracts during bidding. Misclassifying one as the other can void the resulting agreement and expose the architect to a claim of failure to administer the contract correctly. 4 takeaways close the loop on delivery method VE judgment. 5 takeaways from the delivery method VE framework. Design bid build limits value engineering to the design phase, and any post-bid VE lands as a contractor change order with profit markup attached. CMAR provides the most effective VE in practice because the construction manager is on board through design and offers continuous, real-time cost feedback as alternatives surface. Design build folds VE inside the design build team itself, trading design decisions against construction efficiency from day one. And IPD extends that further with shared savings incentives that motivate every party. VECPs are during construction proposals, with savings typically split between owner and contractor, and the architect reviews each one for design intent, code compliance, and performance, not cost. VECPs are not substitutions, different mechanism, different review criteria, and confusing them is one of the cleanest paths to a professional liability claim in contract administration. Most architects who get sued over VE decisions had the same blind spot. They accepted a proposal that claimed to improve quality, cut cost, and shorten schedule with no trade-off. And they never asked which one was actually getting cheated. You cannot have all 3. Quality, cost, and schedule form a triangle, and locking down 2 of the 3 forces the third to adjust. Fast and cheap means lower quality. Fast and high quality means higher cost. Cheap and high quality means a slower schedule. The architect who lets the owner believe all 3 are achievable simultaneously is the architect who explains in a deposition why the building did not perform as promised. The exam tests this directly, and so does professional practice. 5 real VE decisions show how the triangle plays out. Each one trades one axis for the other 2. 5 real VE decisions and how they ripple across the 3 axes. Switching steel to precast concrete typically saves around 10 to 15% on the structural package. That range is illustrative because span and seismic conditions change it, and precast erects faster, so cost and schedule both improve. But the aesthetic shifts, the connection details change, and the project loses some structural flexibility for late changes. Reducing floor-to-floor height saves cladding and riser cost and speeds construction, but compresses ceiling height and MEP flexibility downstream. Combining mechanical rooms eliminates equipment duplication for a cost win and is roughly neutral on schedule, but longer duct and pipe runs introduce noise risk and energy losses. Standard versus custom curtain wall is one of the easiest VE levers. Custom typically costs around 30 to 50% more and has longer lead times, but you lose design expression. Deleting a basement level produces major savings on excavation and waterproofing and shortens the schedule, but the lost program space has to be accommodated somewhere else in the building. Each row trades one axis to improve the others, never all 3. The triple constraint is a definition you should be able to recite because owners need to hear it from you. The triple constraint is the project management definition every architect should be able to articulate to an owner. Quality, cost, and schedule form a triangle. The owner can choose to optimize any 2 of the 3 at a given moment, but the third axis will adjust to accommodate. Fast and cheap usually means lower quality. Fast and high quality usually means higher cost. Cheap and high quality usually means a slower schedule. The architect's job during value engineering is to make every trade-off conscious and documented, never accidental. If the owner believes the proposed VE delivers all 3 improvements with no trade-off, the architect has either failed to identify the real trade-off, or worse, has agreed to a proposal that quietly degraded function in a way that will surface later as a defect claim. Lawsuits over VE-driven failures almost always trace back to an undocumented assumption that all 3 constraints improved simultaneously. 4 warning signs flag a VE proposal that is hiding the trade-off it doesn't want you to see. 4 warning signs that a VE proposal is hiding the trade-off the architect needs to identify before signing off. First, if the proposal claims improvement on all 3 axes, better quality, lower cost, faster schedule, with no stated trade-off, something is wrong. Either the proposal contains a function reduction the proposer did not disclose, or it shifts a long-term cost the analysis ignored. Second, if cost savings exceed roughly 20% without a corresponding scope or quality reduction, the math is suspect. Genuine VE rarely produces savings that large without giving up something meaningful, and an unexamined 20% savings claim is the kind of thing that produces a claim 3 years into operations. Third, when the proposed alternative has shorter lead time, higher quality, and lower costs simultaneously, ask what is being deferred. Frequently, the answer is maintenance cost or replacement cycle, both of which surface after the architect's involvement has ended. Fourth, when the long-term maintenance burden is mentioned briefly or not at all in the proposal, the long-term burden is the trade-off. Read for what is missing, not just what is present. 4 takeaways anchor the way you talk about trade-offs in every VE meeting. 5 takeaways from the triple constraint framework that you can carry into every VE meeting. Quality, cost, and schedule form a triangle, locking down 2 of the 3 forces, the third axis to adjust. And any architect who pretends otherwise is setting up the owner for disappointment. Every legitimate VE decision trades one axis to improve the others, and the exam rewards candidates who can identify which axis is being traded in a given proposal. The best VE improves 2 of 3 constraints without significantly harming the third, and that pattern is what the exam asks you to recognize. Watch for proposals that claim all 3 constraints improve simultaneously. That is where lawsuits start, because the unstated trade-off lands in operations after the architect's involvement has ended. And document every trade-off in writing as it is agreed. Verbal commitments during a VE meeting collapse under the pressure of a defect claim or a fee dispute, and the architect who relied on them is the one explaining the gap to insurance. Most architects who have made a late DD grid change tell the same story. Weeks of redesign, every consultant reissuing drawings, and a quiet conversation with the principal about how to absorb the schedule slip. The structural grid is one of the most consequential early decisions in building design, and it is one of the least reversible. Foundations are sized to it. Lateral system is located by it. MEP risers stack on it, and the facade rhythm responds to it. Once you commit, every discipline downstream commits along with you. Set the grid deliberately, with parking, occupancy, and facade module all considered together. The architect who treats the grid as a structural-only decision gets sued by an owner whose program had to be rebuilt around it. 5 grid considerations interact at the same moment. Each one pulls in a different direction. 5 grid considerations that have to reconcile in DD before the structural drawings advance. Column spacing comes first. Structural engineers want economical spans, typically around 25 to 35 feet in steel and 20 to 30 in concrete. But those spans have to align with the architectural planning module, the corridor widths, and the parking bay if parking sits below. Column size is the second consideration. Larger columns at lower floors carry the gravity load but intrude into usable space, so the resolution is to coordinate column size with wall thickness so the column lives inside the wall rather than projecting into the room. Transfer conditions, where columns above do not align with columns below, are expensive, and the structural engineer avoids them whenever possible. But architectural needs sometimes demand open floor plates below occupied floors, and the team has to decide whether the transfer is worth the premium. Floor-to-floor height trades deeper beams against ceiling height. Deeper beams span farther, but consume the MEP zone, so the resolution is to balance beam depth against the MEP routing the engineer needs. And the lateral system, whether shear walls or braced frames, wants specific locations the architect would rather keep open. So the resolution is to locate lateral elements at stairs, elevators, and party walls where they cost the floor plan less. 5 common grid conflicts surface in every commercial DD. Catching them early is the architect's job. 5 common grid conflicts that show up in commercial DD, and that the architect is responsible for catching before CD issue. First, a column lands in the middle of an open conference room or a key program space, and the only fixes are relocating the column upstream in the structural grid or shifting the program around it, both of which cascade. Second, the parking bay does not divide cleanly into standard parking stalls plus the required drive aisle, leaving wasted space or stranded stalls. The fix is retuning the bay dimension to land cleanly. Third, the curtain wall mullion module fights the structural grid, producing awkward facade joints that read as construction errors even when intentional. Resolution: align mullions to the bay or introduce an intermediate grid that resolves both. Fourth, stair runs hit a column at a landing, and the resolution is to slide the stair, use an offset landing, or relocate the column at the structural grid. Fifth, an elevator shaft conflicts with a shear wall, which forces a choice between repositioning the core or accepting an awkward shaft. Catch these in DD and you fix them on the page. Miss them and you fix them on the construction site, where the cost multiplier is brutal. A universal bay strategy resolves several of those conflicts in one move. Done right, it pays for itself many times over. A universal bay strategy resolves the most expensive grid conflicts in a mixed-use building in one move, and the 4-step process is straightforward. First, identify every floor use in the building stack, typically parking below, then residential or office above, sometimes retail at grade, so the team is solving the full puzzle and not just one floor at a time. Second, map the dimensional needs of each use: parking stall sizes, drive aisle widths, residential or office planning modules, and the span limits each one wants to stay under for cost reasons. Third, find a bay dimension that serves the most expensive use first, usually parking, because parking has the least flexibility on stall and aisle dimensions. Then check that the bay still works for the residential or office uses above. A bay around 27 to 30 feet often lands as a workable universal dimension for parking plus office or parking plus residential stacks. Fourth, verify that the universal bay avoids transfer beams between floor uses. Transfer beams between parking and the floors above are a major cost item, and the whole point of the universal bay strategy is to eliminate them. Done right, the universal bay can save the project significant cost on the structural package. 4 takeaways anchor the grid conversation in every DD milestone meeting. 5 takeaways from the structural integration framework. The grid is almost irreversible after DD because foundations, lateral system, MEP risers, and the facade rhythm all commit to it, so set it deliberately, with parking and occupancy and facade module all considered together. 5 grid considerations must reconcile during DD: column spacing, column size, transfer conditions, floor-to-floor height, and lateral system location, and each one pulls in a different direction. 5 common grid conflicts predict where the drama lives: column in the open room, parking bay misfit, mullion grid clash, stair column collision, and elevator shear wall conflict. And catching them in DD rather than in construction administration is the architect's job. The universal bay strategy serves multiple floor uses with one structural grid and eliminates transfer beams between uses, often saving significant structural cost on mixed-use buildings. And locating lateral elements at stairs, elevators, and party walls keeps them out of the open floor plate, which is where they cost the architecture the most. Most architects who get sued over coordination failures had the same blind spot. They treated MEP space allocation as a consultant problem instead of an architectural decision. MEP systems consume around 15 to 25% of a building's gross area and a significant portion of every floor-to-floor height. The most expensive sentence in construction is the one a contractor speaks in CA. There is not enough room in the ceiling for the ductwork. That sentence means either the floor-to-floor height has to increase, which is structural redesign, or the duct routing has to change, which is MEP redesign. And both produce a flood of RFIs, change orders, and arguments about who pays. You are personally on the hook if the architect's coordination role was not performed competently, and the resulting lawsuit lands on professional liability coverage. 6 rules of thumb anchor every MEP space allocation conversation. Memorize them. 6 space allocation rules of thumb that every architect uses during DD. Main mechanical rooms typically consume around 3 to 8% of gross floor area, depending on system type, and they need 12 to 16 feet of clear height plus access for major equipment replacement when the chiller or air handler reaches end of life. Electrical rooms are usually around 200 to 400 square feet per typical floor, and the NEC requires a minimum 36-inch working clearance in front of every panel, which the architect must protect on the plan. Telecom and data rooms run around 150 to 300 square feet per floor, ideally stacked vertically, with a minimum of 10 by 12 feet per floor to allow for racks and cable management. The ceiling plenum is typically 18 to 36 inches above the finished ceiling, and that depth has to accommodate ducts, piping, conduit, sprinkler mains, and structural depth all at once. Vertical chases consume roughly 2 to 4% of floor area and must align continuously floor to floor for the risers to work. And plumbing walls need 6 to 8 inches minimum thickness, with wet rooms stacked vertically to minimize horizontal runs that complicate every floor below. 6 steps in the right order make MEP coordination work in DD. Skip them and you redesign in CD. 6 steps run MEP coordination during DD. And the sequence matters. First, the architect proposes the floor-to-floor and ceiling height target before any consultant commits to system sizing, because the target is what every other discipline plans against. Second, the structural engineer confirms beam depth at the primary spans for that target. If the beam depth would consume the MEP zone, the conversation about floor-to-floor restarts before the MEP engineer wastes time routing ducts that will not fit. Third, the MEP engineer routes the main duct trunks and flags tight spots back to the team. The architect now knows where conflicts will surface and which routes need protection. Fourth, the architect locates plumbing chases, electrical rooms, and telecom rooms with input from each consultant, so the equipment room footprint matches the equipment that will live there. Fifth, the reflected ceiling plan is reconciled with MEP equipment, lighting fixtures, sprinkler heads, and access panels, because the RCP is the single drawing where every system collides. Sixth, run clash detection before issuing DD and resolve every remaining conflict on the page. Never carry an unresolved clash into CD. 4 floor-to-floor traps wait for architects who skip that sequence. Each one is expensive. 4 traps that catch architects who skipped the coordination sequence. First, beam depth gets committed before the MEP zone is sized, and when MEP routing requires more plenum depth than the structural depth left available, the structural engineer either has to redesign beams or the architect has to absorb the floor-to-floor change. Both are expensive in late DD. Second, the plenum depth is budgeted for ductwork only, and then sprinkler mains, electrical conduit, fire alarm cable, and acoustic isolation get layered in afterward, and the plenum no longer holds it. The architect gets sued by an owner who paid for usable ceiling height that did not survive coordination. Third, equipment room floor-to-floor is matched to office floors above by default. And when the MEP engineer specifies an air handler that needs 16 feet of clear height, the architect discovers the mismatch in DD and pays to redesign. Fourth, floor-to-floor gets reduced in VE without rechecking MEP clearances. The cost savings look attractive on paper, and the clashes appear in CA when the contractor tries to route ducts through the compressed plenum. 4 takeaways tighten the MEP space allocation conversation in every DD milestone. 5 takeaways from the MEP coordination framework. MEP consumes around 15 to 25% of a building's gross area, and that allocation has to be deliberate in DD rather than assumed away. 6 rules of thumb cover the major spaces: mechanical rooms, electrical rooms, telecom rooms, ceiling plenum, vertical chases, and plumbing walls. And every architect should be able to size these without looking them up. The 6-step coordination sequence runs in order. Architect proposes floor-to-floor and ceiling height first. Structural confirms beam depth. MEP routes the main trunks. Architect locates the equipment rooms. Reflected ceiling plan reconciles every system, and clash detection runs before DD issue. Floor-to-floor height is the single most consequential MEP coordination dimension, and reducing it in VE without rechecking MEP clearances is one of the most common pathways to a coordination claim. And finally, run clash detection before issuing DD and resolve every conflict on the page. Carrying unresolved clashes into CD is professional negligence. Every architect who has been deposed over a commercial envelope failure heard the same opening question. Walk us through the detail where the cladding meets the structure. That single interface is the most technically demanding zone in the entire building because 4 different design disciplines all converge on it. The thermal insulation has to stay continuous, the air barrier has to stay continuous, the moisture management has to stay continuous, and the structure has to deflect without dragging the envelope with it. Miss the coordination on any one of those 4, and the resulting failure is the most expensive defect category in commercial construction. Mold remediation runs into the millions, curtain wall replacement runs into the millions, and the architect's professional liability policy gets a phone call. The exam tests this interface aggressively because the candidates who do not understand it become the architects who get sued for it. 5 interface problems show up on every commercial project. Know each one before you draw the wall section. 5 interface problems show up on almost every commercial project, and each one has a known design solution that the exam expects you to recognize. Thermal bridging at slab edges happens when the floor slab pokes through the insulation plane and acts as a giant cooling fin to the outside. The fix is an insulated slab edge detail, or thermal brake clips that interrupt the conduction path. Steel lintels over openings do the same thing on a smaller scale, conducting heat right past the wall insulation. Thermally broken lintel assemblies solve it, and most curtain wall manufacturers now offer them as standard. Air barrier continuity breaks down at beam-to-column connections, where the membrane has to wrap around steel that the structural engineer never asked the architect about. The detail is a continuous air barrier membrane lapped and sealed at every penetration. Differential movement happens because steel deflects under load, and masonry does not, so the cladding cracks unless the architect designs in soft joints with shelf angles on slotted connections. And waterproofing at grade is the spot where the below-grade wall meets the above-grade envelope. That transition needs a continuous waterproofing lap, not 2 separate systems that meet and hope. 6 integration principles run underneath those 5 fixes. They are the rules every wall section has to obey. 6 principles govern every legitimate envelope structure detail, and the exam treats them as testable rules rather than guidelines. First, the air barrier. The vapor retarder and the thermal insulation must stay continuous from the foundation to the roof. Any gap is a path for air, water, or heat, and the gap usually ends up being the source of the future claim. Second, any structural element that crosses the insulation plane creates a thermal bridge, and the architect either designs it out by relocating the structure or thermally breaks it with engineered isolation clips. Third, shelf angles that support masonry have to accommodate structural deflection, and the standard is typically L/600, meaning the cladding has to tolerate the frame deflecting that amount without cracking. Fourth, Window and curtain wall anchors must coordinate with the structural frame before frame sizes lock, because anchor locations drive structural reinforcement at the slab edge. Fifth, cladding expansion joints must align with structural expansion joints. If you offset them, one of the two will crack. Sixth, flashing and drainage planes have to be detailed at every floor line and every opening, not assumed away as a contractor responsibility. One pitfall hides inside almost every modern energy model: the steel stud wall that performs 40% worse than the calculator predicts. Thermal bridging is the single most underestimated number in commercial envelope design, and the gap between the calculator and the field is wide enough to cost real money. A steel stud wall with continuous insulation can lose roughly 40% more heat than the R value alone suggests, because every steel stud is a tiny radiator passing heat from inside to outside. ASHRAE 90.1 and the IECC both require continuous insulation specifically to address this. They recognize that traditional cavity-only insulation overstated wall performance by margins that hurt national energy targets. The bridges themselves show up in predictable places: slab edges, lintels over openings, shelf angles supporting masonry, parapets, and balcony slabs that cantilever out through the wall plane. Each is a known detail with a known solution, and the architect who treats them as known is fine. The architect who passes them off to the consultant gets a phone call when commissioning catches an envelope that underperforms the energy model by a margin the owner blames on the design team. The lawsuit traces back to whether the architect drew the bridge correctly, not whether the contractor built what was drawn. 5 takeaways anchor the way you should review every envelope structure detail going forward. 5 takeaways close the envelope structure interface section. The same 5 interface problems repeat on almost every commercial project: slab edge bridging, steel lintel bridging, air barrier gaps, differential movement, and grade line waterproofing. And each one has a known solution rather than a creative one to invent. The air barrier, the vapor retarder, and the thermal insulation must stay continuous from foundation to roof, because any structure crossing the insulation plane becomes a thermal bridge that wrecks measured performance. Differential movement between steel and masonry has to be designed for explicitly, with soft joints and shelf angles on slotted connections, never assumed away. ASHRAE 90.1 and the IECC both require continuous insulation specifically because traditional cavity-only insulation overstated wall performance by margins that hurt national energy targets. And finally, the exam tests whether you can recognize when thermal bridging is hurting building performance and choose the detail that fixes it, not whether you can recite the R value formula. The architect who reads wall sections looking for bridges catches the future lawsuit before it leaves the drafting table. Every architect who has tried to move an elevator after construction documents knows what happens. The shaft does not move by itself. The structural frame around it has to redesign. The MEP risers serving it have to redesign. The rated wall assemblies tying into it have to redesign, and every floor plan that referenced its location has to redesign. The same thing happens when you try to relocate a stair, a sprinkler riser, or a smoke control shaft. Vertical transportation and fire protection systems have rigid code requirements, and they have to be integrated during DD, rather than added in afterward. Owners who watch their schedules collapse because the architect treated fire protection as a consultant deliverable will sue, and the architect ends up personally liable for the redesign cost when the professional liability deductible runs out. Worse, a sprinkler coverage gap or a smoke barrier in the wrong place produces injuries during a real fire event, and that is the lawsuit that closes architectural practices. The exam asks the same question over and over. When do you fix the location of the stair, the elevator, and the sprinkler risers? And the answer is DD, not CD. 6 systems carry hard architectural impact: Know the integration issue for each before DD issue. 6 systems each carry hard architectural impact that the architect cannot delegate away. Elevators are defined by shaft size, pit depth, and overhead clearance. And once those numbers are set, the shaft location affects every floor plan in the building, because the shaft is the one thing that cannot move floor by floor. Stairs are defined by width, landing size, and travel distance limits, and most occupancies require at least 2 stairs separated by minimum distance, which means the stair location drives the egress diagram before the floor plan does. Sprinklers are defined by head spacing, obstruction rules, and pipe routing, and the ceiling layout has to accommodate sprinkler heads, or the reflected ceiling plan gets thrown out and redrawn. Fire alarm devices have to land at specific visual and audible coverage locations that affect the finished ceiling pattern. Smoke control needs dedicated pressurization shafts and smoke barriers built out of rated construction. None of that fits inside leftover space. And standpipes need riser locations in the stairs with hose connections at every floor, which means the stairwell dimensions have to accommodate standpipe equipment from DD forward. Elevators carry the single largest architectural footprint. 6 rules cover the integration. 6 elevator integration requirements every architect should be able to recite from memory in DD. First, machine roomless elevators still require dedicated overhead space and pit depth. The marketing line that they save space is true at the equipment room level, but not at the shaft level. And architects who plan the shaft as a simple vertical box discover the overhead and pit requirements during shop drawing review. Second, elevator lobbies may be required for fire service access, depending on building code and occupancy. Some codes require them for high-rise buildings, hospitals, and certain assembly occupancies. Third, shaft walls are typically 2-hour fire-rated construction in commercial buildings, which means the wall assembly has to be coordinated with the architectural finishes around it. Fourth, venting requirements vary by code. Pressurized shafts require a separate fan system and ductwork, while vented shafts require a relief opening at the top, and the details are not interchangeable. Fifth, the structural loads from elevator equipment require early coordination with the structural engineer because the loads land at specific points the engineer needs to know about during structural sizing. Sixth, ADA and ICCA 117.1 dictate minimum cab sizes and door widths, and those numbers drive the shaft dimensions, not the other way around. Sprinklers and smoke control add their own layer. 3 rules anchor the coordination. Sprinklers and smoke control are the integration touchpoint that catches architects who treat fire protection as a consultant problem. NFPA 13 governs sprinkler head spacing, obstruction rules, and clearance distances, and the reflected ceiling plan has to respect those numbers, which means the architect coordinates the RCP against the sprinkler design, not the other way around. Smoke barriers have to be drawn architecturally and called out on the plan as smoke barriers because they have construction and continuity requirements that no consultant draws for you. Stair pressurization requires HVAC system design coordinated with the architectural shaft, including a dedicated supply fan, dedicated ductwork, and tested pressure differential at every door. None of that fits inside a regular shaft. Fire-rated penetrations have approved listed assemblies that come from manufacturers, and the architect specifies the listing. Never invent the detail, because anything not listed is not approved. And finally, integrate fire protection in DD, not in CD. Adding sprinkler coverage in CD triggers reflected ceiling plan rework that cascades into lighting, MEP, and acoustic redesign. And the architect typically absorbs the rework cost because the CD was the place to catch it. 5 takeaways tie the integration story together for the next DD review. 5 takeaways for the vertical transportation and fire protection integration framework. 6 systems each carry hard architectural impact: elevators, stairs, sprinklers, fire alarm, smoke control, and standpipes. and the architect has to fix every one of their locations in DD rather than CD, because moving any of them in CD produces cascading redesign costs. Elevator shafts cannot move floor by floor. The shaft is the one architectural element that has to align vertically from pit to overhead, and the architect sets it once with structural input rather than 3 times. Stair locations drive the egress diagram before the floor plan locks, because travel distance limits and the 2-stair separation rule constrain where the floor plan can put corridors. NFPA 13 sprinkler spacing controls the reflected ceiling plan. The architect coordinates the RCP against sprinkler design rather than expecting the sprinkler designer to work around finishes. And finally, fire protection is integrated architecture, not a consultant add-on. The architect who treats it as the latter watches the schedule die. The architect who treats it as the former delivers a coordinated set. Most architects who try to write a performance specification end up with a sales brochure dressed up as a spec. Language that sounds technical, but is not actually testable in the field. Performance specifications define what results are required without dictating how to achieve them. And they exist because the contractor or manufacturer is in a better position to choose the recipe. The transfer of method choice to the contractor is also a transfer of method risk, which is exactly what the architect wants on assemblies where multiple manufacturers can deliver. But the transfer only works if the architect defined the result in measurable, testable terms with an acceptance procedure attached. A performance spec that says, high-quality finish or industry-standard fastening is not a performance spec. It is an invitation for the contractor to deliver the cheapest option that arguably meets the wording, and for the architect to be sued over what the spec actually meant when the owner's curtain wall leaks in year 3. The wrong word in a performance spec is also a wrong answer on the exam. And candidates who confuse measurable performance with marketing language fail the exam section every cycle. 6 measurable criteria show up in every legitimate performance spec. Each one has a published test method. 6 performance criteria show up in almost every commercial spec section, and each one has a published test method that gives the result a number you can verify in the field. Thermal performance is specified by U value, solar heat gain coefficient, and R value of the assembly, and the verification is ASTM test methods plus thermal modeling for whole assembly performance. Structural capacity is specified by load rating, deflection limits, and wind resistance, verified by structural calculations and load testing on built mock-ups. Acoustic performance is specified by sound transmission class, impact insulation class, and noise reduction coefficient, verified by ASTM lab and field testing, with the field number always lower than the lab number. Air infiltration is specified as a leakage rate in cubic feet per minute per square foot at a specified pressure differential, verified by ASTM E783 field testing of the actual installed assembly. Water penetration is specified as no leakage at a specified pressure and duration, verified by AAMA 501 or ASTME 1105 field testing on the installed envelope. And fire resistance is specified by hourly rating of the assembly, verified by UL design number or ASTME 119 test. 6 criteria, 6 test methods, no ambiguity. 6 rules separate a real performance spec from a sales brochure. Each one matters in court. 6 rules separate a legitimate performance spec from a wishful one, and the exam tests every one of them. First, define measurable, testable criteria. High-quality finish is not a criterion. 50 STC minimum is. Second, specify the test method and acceptance standard explicitly rather than implicitly, because if you do not name the test method, the contractor will choose the easiest one to pass. Third, Include the environmental conditions under which performance is measured. Air leakage at 75 pascal pressure differential is a specification. Air leakage in general is not. Fourth, require submittals demonstrating compliance before fabrication begins, because catching a non-compliant product in submittal review is cheap, and catching it after installation is expensive. Fifth, include mock-up and field testing requirements for critical assemblies, the curtain wall, the roof, the sound-rated demising wall, because lab numbers always look better than field numbers, and only field testing tells you what the building actually delivers. Sixth, define remediation procedures when performance criteria are not met, so there is a clear contractual path forward when the test fails, rather than a fresh argument with the contractor over who pays for the fix. Performance specs are powerful, but only on the right assemblies. Pick the wrong one and you create the problem you tried to solve. Choosing whether to write a performance spec is itself a design decision, and the exam tests whether you make it deliberately. Performance specs work well on assemblies where multiple manufacturers can meet the goal. Curtain wall systems, sound-rated demising walls with an STC number, roofing membranes where life and warranty are the testable result, and exterior insulation systems where R value and air leakage drive the manufacturer choice. In those cases, the contractor gets to optimize, and the architect gets the result. Performance specs work poorly on items integral to the architect's design intent. Custom architectural millwork is not interchangeable. A specialty plaster finish the architect designed personally is not interchangeable. An owner-specified light fixture for a branded space is not interchangeable. And items with a single supplier or limited supplier market are not interchangeable. On those items, write prescriptive or proprietary specs and stop pretending the market is open. The architect who writes a performance spec on the wrong item gets a substitution request for the cheapest thing that arguably meets the wording, and the architect's design intent walks out the door. 5 takeaways anchor the specification strategy conversation in the next DD review. 5 takeaways close the performance specification framework. Performance specs define outcomes rather than methods, and they only work when the outcomes are testable in the field. Every performance specification is a downstream test waiting to happen. 6 criteria families show up across almost every commercial project: thermal, structural, acoustic, air infiltration, water penetration, and fire resistance. And each one has a named test method that produces a verifiable number. 6 rules separate a real performance spec from a wishful one: measurable criteria, named test method, environmental conditions, submittal requirements, mock-up and field testing, and remediation procedures when results miss the target. Performance specs are the right tool for interchangeable assemblies where multiple manufacturers can meet the goal, and the wrong tool for design intent items where the architect needs control over the specific product. And finally, vague performance language is unenforceable. If you cannot test it in the field, do not write it as a performance spec, because the dispute that follows costs more than the prescriptive language would have. Substitution management is the spec coordination task that most architects underestimate, and the underestimation shows up as a flood of substitution requests in the first 30 days after bid award. The specification has to clearly define when substitutions are permitted, what documentation the contractor has to submit with the request, who bears the cost of evaluating the alternative, and what happens to the design intent if the substitution is denied. Silence on any of those points is the path to a fight. When the spec says nothing about substitutions, the contractor reads the spec the way the contractor wants to read it, and the architect spends weeks evaluating products for free that the contractor proposed to save themselves money. A well-drafted substitution clause channels the conversation, sets the documentation bar, and protects the architect's fee. The exam tests whether you understand the timing categories and the approval process for each one, because the right answer depends on when the substitution arrives. 4 substitution categories drive every approval decision. Timing determines the process. 4 substitution types each follow a different approval process, and the determining factor is timing, when the request arrives. Pre-bid substitutions land before the bid date, typically with a window of 10 or more days to allow evaluation. If approved, the answer goes out as an addendum to all bidders, so the playing field stays level. Post-bid, pre-award substitutions land after the bid opens but before the contract is signed, and the review has to be careful because the substitution may affect the bid evaluation. If bidder A bid the original product and bidder B bid the substitute, accepting the substitute changes the comparison and may require rebidding. Construction substitutions arrive after contract award and require a formal submittal with full documentation of equivalence, plus architect review against design intent. The contractor pays for the review and absorbs the cost of any required redesign. VECP substitutions, value engineering change proposals, arrive during construction and require cost analysis plus a shared savings agreement, where the owner and contractor split any savings generated by the substitution. Each type has a different paper trail, and the architect manages them by category rather than treating every request the same way. Product representation and warranties carry their own rules. 6 anchor the conversation. 6 rules cover product representation and warranties, and the exam tests several of them every cycle. First, manufacturers provide product data, test reports, and samples for architect review, and the architect reviews them against the spec, not against the architect's own preferences. Second, shop drawings are the contractor's interpretation of the design, and the architect reviews them for conformance with design intent, rather than approving them as means and methods. Third, the standard general warranty under AIAA 201 is 1 year from substantial completion, which covers most of the construction work as a baseline. Fourth, extended warranties for roof, waterproofing, and windows are specified separately by the architect in the appropriate spec sections: a 10-year roof warranty, a 20-year window warranty, and so on. And those start at substantial completion as well. Fifth, the warranty start date is typically substantial completion rather than installation, which matters when an element gets installed early and sits exposed for months before the building is substantially complete. Sixth, manufacturer warranties cover the product itself, while contractor warranties cover the installation quality. They are different warranties from different parties, and a failure in the field can trigger one, the other, or both depending on root cause. One single word on the shop drawing stamp can shift liability. The wrong word costs the architect's defense. The single word the architect writes on the shop drawing stamp can shift legal liability, and most architects who get sued over shop drawings used the wrong word. Approved is the wrong word. It implies the architect endorsed the contractor's means and methods, and that endorsement transfers liability for means and methods failures back to the architect. The professional liability policy will tell you the same thing. Reviewed or no exceptions taken is the right language for shop drawings that conform to design intent. It documents that the architect looked at the package and found no exceptions to call out, while keeping liability for the contractor's chosen approach where AIAA 201 puts it with the contractor. Furnish comments documents the review without endorsing the contractor's choices, used when the architect wants to flag observations but not block the work. Rejected or revise and resubmit returns the package for correction when the architect cannot accept what is on the page. And finally, the architect reviews for conformance with design intent rather than for accuracy of dimensions. The contractor is responsible for verifying dimensions at the site, and the architect's review is not a check of the contractor's measurements. 5 takeaways close the substitution and shop drawing framework before the next submittal lands. 5 takeaways close the substitution and product representation section. 4 substitution types are categorized by timing: pre-bid handled via addendum, post-bid and pre-award handled with careful review because bid evaluation may change, construction substitutions handled with formal submittal and architect review, and VECP substitutions handled with cost analysis and shared savings agreements. Substitution clauses must define documentation requirements, who bears the cost of evaluation, and the timing for response. Silence on any one of those invites the disputes that consume the first 30 days of construction. The standard AIAA 201 warranty is 1 year from substantial completion, and extended warranties for roof, waterproofing, and windows are specified separately by the architect. Manufacturer warranties cover the product, while contractor warranties cover the installation, and a failure can trigger one or both depending on root cause. And finally, stamp shop drawings as reviewed, or no exceptions taken, never as approved, because the word approved transfers means and methods liability back to the architect, and the architect's professional liability policy was never priced for that transfer. Specification drawing coordination is one of the most error-prone areas of construction documentation, and almost every architect who has been sued over a documentation defect was sued over a coordination gap rather than a design error. Conflicts between drawings and specifications generate RFIs, change orders, and disputes during construction administration, and the architect has to interpret each one without the documents in their favor. The economics are simple. An RFI costs the architect roughly $400 to $1,500 in unbillable time, and a project with 200 coordination RFIs consumed the project's profit margin before the contractor even mobilized. Worse, when the contractor uses ambiguous documents to back out of scope, the owner sues the architect for the cost differential, and the lawsuit centers on whether the documents were coordinated. A systematic coordination process during DD and CD phases is the only path to a defensible set, and the exam tests whether you know what that process looks like. 4 conflict types repeat on every commercial project. Each one has a prevention strategy that closes it on the page. 4 conflict types repeat on almost every commercial project, and each one has a known prevention strategy. The first is product naming. The drawing calls out one product, and the spec calls out a different one, and the contractor gets to pick whichever is cheaper. The fix is to use keynotes on the drawings that reference spec section numbers, not product names, so the drawing points at the spec, and the spec stays the single source of truth. The second is a quantity conflict. The plan shows 4 roof drains, and the spec says 6, leaving the contractor to argue for the lower number. The fix is the CSI rule, that drawings show quantity and specs describe quality, with no duplication between the two. The third is a detail conflict. The wall section shows rigid continuous insulation, and the spec says batt insulation, and the contractor installs whichever is cheaper. The fix is a cross-reference of every detail against its spec section during QC review, before the set issues. The fourth is a scope gap. Neither the drawings nor the specs address a transition detail, and the contractor either improvises and bills for it later, or refuses to build it without a change order. The fix is a responsibility matrix that assigns every scope element to a drawing or a spec section, so no element falls between the two. 5 practices anchor the coordination workflow at every milestone. The exam tests each one. 5 coordination best practices separate a defensible set from a litigation magnet, and the exam tests each one as a standalone rule. First, use keynotes on drawings that reference master format section numbers in the specifications. The drawing points at the spec rather than duplicating it, and updates flow one way instead of in 2 places that drift apart. Second, maintain a drawing specification cross-reference log throughout the project, updated at every issue, so the team can trace every drawing element back to its governing spec section. Third, never put product names or model numbers on drawings. They belong exclusively in specifications, because product information drifts at every addendum and the drawings cannot keep up. Fourth, review specifications and drawings simultaneously during QC rather than independently. A QC reviewer who looks at drawings without specs catches half the errors, and vice versa. And the architect who relies on independent reviews creates exactly the conflicts the process was supposed to catch. Fifth, use not in contract designations carefully. Owners or other contracts have to actually cover the scope, and a careless NIC creates a scope gap that the contractor will refuse to fill without a change order, and the lawsuit that follows traces back to the careless designation. 1 AIAA 201 rule governs every conflict that survives QC. Know it before the contractor uses it against you. 1 AIAA 201 rule governs every drawing spec conflict that survives QC, and the rule is the single most tested item in this entire section. Under AIAA 201, Article 1, drawings and specifications are complementary. What is required by either is required by both, and there is no automatic precedence of specs over drawings or vice versa. The widely cited myth that specs always govern over drawings is wrong on the default contract, and candidates who answer that way on the exam fail the question. When conflicts exist in the documents, the contractor must request clarification through an RFI, and the architect interprets the conflict and issues the controlling answer. The architect's interpretation has contractual weight under A201, which is why the architect is the named interpreter rather than the owner. Custom supplementary conditions, written into a specific project's contract, can override the default rule and establish a precedence order. And those project-specific overrides are the exception, not the rule. Read the contract before assuming default. A 201 applies because the architect who relies on the default and gets surprised by a supplementary condition spends the dispute on the wrong side of the language. 5 takeaways close the drawing spec coordination conversation for the next document issue. 5 takeaways close the drawing spec coordination framework. 4 conflict types repeat on almost every project: product naming, quantity conflicts, detail conflicts, and scope gaps. And each one has a known prevention strategy rather than a creative one to invent. Use keynotes on drawings that reference master format section numbers, and keep product names and model numbers in the specifications only, because that is where they belong, and that is where addenda update them. QC reviews specifications and drawings together rather than independently, because the conflicts only show up when the two are compared, and reviewing them in isolation catches less than half of the errors. AIAA 201 makes drawings and specifications complementary, with no automatic precedence. The specs over drawings myth is the wrong answer on the exam and the wrong defense in a dispute. And finally, when a conflict reaches construction, the contractor RFIs it, the architect interprets it, and the architect's interpretation is the controlling answer under the contract. The architect who runs the coordination process closes the conflicts on the page rather than absorbing the lawsuit later. Every architect who has worked on a project for 6 months stops seeing parts of it. The basement waterproofing detail that everyone assumed was resolved, the door schedule discrepancy that nobody rechecked after the program shifted, the egress count that needs a new occupancy classification. These become invisible to the team that lives inside the project. Peer review exists because outside eyes see what inside eyes miss. An independent, qualified professional examines the design documents for errors, omissions, code compliance, and design adequacy. And the reviewer brings fresh perspective without investment in any of the prior design decisions. This is different from internal QC, where senior staff inside the firm review the work. Internal QC catches drawing accuracy and standards conformance, but it cannot see around the assumptions the team has been making since schematic design. When peer review catches a code violation post-permit, the architect is personally liable for the redesign cost and the schedule overrun. And the owner's lawsuit names the architect, rather than the building department. Catching the violation before permit is cheap. Catching it after is expensive. 4 review types each do a different job. Knowing which one to commission and when is itself a design decision. 4 review types each do a different job, and the architect commissions them on different schedules. Internal QC review is performed by senior staff within the firm at milestones in each phase, typically end of SD, end of DD, and at the 50% and 95% CD marks. The focus is drawing accuracy, coordination between drawings and specs, and conformance with firm standards. Independent peer review is performed by an outside architect or engineer with no investment in the project, typically at the end of DD or in mid-CD. The focus shifts to code compliance, design adequacy, and constructability, the things that are easier to spot when you did not author them. Owner's independent review is performed by the owner's consultant or construction manager at each phase submission, and the focus is budget compliance, program compliance, and quality. These are the owner's interests being protected, not the architect's. Agency or code review is performed by the building department and the fire marshal at CD submission for permit, and the focus is strictly code compliance and life safety. Each review type catches a different category of error, and the architect who runs all 4 catches almost every category. 7 topics belong on every effective design review checklist. They cover the categories that produce claims. 7 topics belong on every effective design review checklist, and each one corresponds to a category of claim the architect's professional liability carrier has paid out before. Code compliance covers occupancy classification, construction type, egress, and accessibility, where the IBC and ADA together produce the largest share of post-permit redesigns. Structural architectural coordination covers grid alignment and clearances. Column locations that drift between A and S drawings produce the second largest share of RFIs. MEP architectural coordination covers equipment rooms, plenum depth, and access panels, since underallocated MEP space is the most common source of CA change orders. Building envelope coverage examines air barrier continuity, thermal bridging at slab edges and lintels, and moisture management at every interface, because envelope failures are the most expensive defect category by far. Life safety coverage examines sprinkler coverage, fire-rated assemblies, and smoke barriers. Gaps here can produce injuries and the lawsuit that closes the practice. Specification drawing consistency cross-references key details, catching the same conflicts the CDQC should have caught. Sustainability coverage examines energy code compliance and LEED credit documentation. The energy code is enforceable, while LEED is contractual. Peer review is not free QC. 3 management rules anchor every peer review engagement. 3 rules anchor every peer review engagement, and the architect who follows them gets value rather than overhead. First, peer reviewers find errors and bill by the hour to do so. Their job is to find problems, and the report typically lands with between 30 and 100 comments. Most comments are legitimate, some are debatable, and a few will turn out to be wrong because the reviewer did not have full context. Plan for that volume in advance and budget review time on the architect's side. Second, the architect triages comments rather than incorporating every one uncritically. Legitimate comments get implemented, debatable comments get a written response explaining the design rationale, and wrong comments get a polite written rebuttal. Some peer review comments will conflict with owner direction or with scope decisions that have already been made, and those have to be managed like RFIs rather than dropped into the documents. Third, some jurisdictions and programs require peer review by an independent, qualified professional. High-rise structures, hospitals, schools, and federal projects all have peer review requirements, and the rules vary by jurisdiction. Verify whether the project falls into a mandatory peer review category early in SD, because discovering the requirement at permit submission delays the schedule and the architect absorbs the cost, while the owner files a claim for the lost time. 5 takeaways close the design review framework for the next phase submission. 5 takeaways close the design review framework. 4 review types each catch a different category of error. Internal QC catches drawing accuracy and coordination. Peer review catches code and constructability. Owner review catches budget and program. And agency review catches code and life safety at permit. The architect who runs all 4 catches almost every category of error before it reaches construction. Independent peer review brings fresh eyes to a project the team stopped seeing. The basement detail everyone assumed was resolved. The egress count the program shift made wrong. 7 checklist topics cover the categories that produce claims: code compliance, structural architectural coordination, MEP architectural coordination, building envelope, life safety, specification drawing consistency, and sustainability. Peer review reports typically land with 30 to 100 comments, and the architect triages them rather than absorbing every one uncritically. Legitimate gets implemented, debatable gets a written response, wrong gets a polite rebuttal. And finally, some jurisdictions and project types require independent peer review. Verify in SD, not at permit submission, because discovering the requirement at the last minute delays the schedule and the architect absorbs the cost of the lawsuit that follows. Most architects underestimate just how many consultants you end up coordinating on a real commercial project. A typical job has somewhere between 8 and 12 consultants producing documents simultaneously. Structural, mechanical, electrical, plumbing, fire protection, civil, landscape, acoustics, interior design, lighting, technology, and code review. And the architect is responsible for coordinating all of them into a coherent set. Coordination failures are the single leading cause of RFIs and change orders during construction. And the architect who fails to lead coordination becomes the architect who gets sued when the building goes up with conflicts baked in. The legal frame is straightforward. Under AIAB 101, the architect's basic services include coordination of consultants, and the owner is entitled to expect that the documents work together. When they do not, the owner's lawsuit names the architect, and the architect's professional liability carrier pays out the cost differential, which usually exceeds the entire design fee for that phase. BIM does not eliminate coordination errors. It makes them visible earlier, but the architect still has to lead the meetings, assign action items, and verify resolutions. The exam tests whether you know that distinction, because candidates who answer that BIM solves coordination fail the question. 5 interface categories produce most coordination failures. Each one has a documented prevention strategy. 5 interface categories produce most multidiscipline coordination failures, and each one has a documented prevention strategy. Architectural structural coordination breaks down when column locations differ between A and S drawings. The prevention is a shared BIM model with a linked structural grid, so both disciplines reference the same coordinates. Architectural mechanical coordination breaks down when ceiling height conflicts with duct routing. The prevention is establishing plenum depth early in DD and running clash detection before issue. Architectural electrical coordination breaks down when electrical panel locations conflict with the architectural layout. The prevention is coordinating electrical room sizes during DD so the rooms fit the equipment rather than the other way around. Structural mechanical coordination breaks down when MEP penetrations through beams are not coordinated. The prevention is requiring the MEP engineer to locate penetrations on the structural drawings where the structural engineer can review and approve them. Civil architectural coordination breaks down when the building's finished floor elevation does not match site grading. The prevention is verifying finished floor elevation against the civil grading plan at every phase milestone, because the two disciplines drift apart unless they are checked. A 6-step workflow runs the coordination process from DD through CD. Each step is non-negotiable. 6 steps run the coordination workflow from DD through CD, and the steps are not optional. First, establish a single coordination model in BIM with linked discipline files. Each consultant works in their own file, and the architect links them into one model where conflicts become visible. Second, issue weekly clash reports during active DD and resolve every clash before the next issue. The discipline of weekly resolution is what keeps the model honest, because clashes that linger become clashes everyone forgets. Third, maintain a coordination log that lists every open issue, the owner of the issue, the target resolution date, and the current status. Without a log, issues drop, and a dropped issue becomes the change order in CA. Fourth, run a dedicated drawing spec cross-check at each major issue milestone: DD issue, CD 50%, CD 95%. Because the conflicts between drawings and specs only show up when you compare them, and the architect is the only party with both sets in hand. Fifth, verify the CD set against an integration checklist before stamping and sealing. Once stamped, the architect owns the documents under licensure law, and the stamp is also the trigger for personal liability if the documents fail. Sixth, track RFI patterns from prior projects, because the firm's most common errors should drive the next project's QC checklist. One contract precedence myth survives every exam cycle. Kill it before it costs you the question. One contract precedence myth survives every exam cycle, and candidates who get the question wrong fail the section. Under AIAA 201-2017, Article 1, drawings and specifications are complementary. What is required by either is required by both, and there is no default precedence of specs over drawings or drawings over specs. The widely cited specs always govern rule is a myth, and the correct exam answer is that the documents are complementary and the architect interprets conflicts. When a conflict surfaces in construction, the contractor reports it via RFI. The architect interprets it, and the architect's interpretation is contractually binding under A201, unless the contractor contests it through the dispute resolution procedures. The interpretation is also what the architect's professional liability carrier defends in the event of a claim, so the architect needs to make defensible interpretations rather than convenient ones. Custom supplementary conditions can establish a precedence order for a specific project, and those project-specific overrides do exist in some contracts. But they are the exception rather than the rule, and the architect has to read the supplementary conditions before assuming default A201 applies. The architect who gets surprised by a supplementary condition mid-dispute spends the case on the wrong side of the contract language. 5 takeaways close the multidiscipline coordination framework for the next consultant kickoff. 5 takeaways close the multidiscipline coordination framework. 8 to 12 consultants produce documents simultaneously on a typical commercial project, and the architect leads coordination under AIAB 101 Basic Services. 5 interface categories cover most coordination failures: architectural structural, architectural mechanical, architectural electrical, structural mechanical, and civil architectural, and each one has a documented prevention strategy rather than a creative one to invent. A 6-step workflow runs the process from DD through CD: single BIM coordination model, weekly clash reports, coordination log, drawing spec cross-check at each milestone, integration checklist before CD issue, and RFI pattern tracking from prior projects. BIM makes coordination errors visible earlier, rather than eliminating them, and the architect still has to lead meetings, assign action items, and verify resolutions. The candidate who answers that BIM solves coordination fails the question on the exam. And finally, AIAA 201 makes drawings and specifications complementary with no automatic precedence. Kill the specs over drawings myth before it costs the architect the question on the exam and the dispute on the project. Most architects underestimate how much scope creep will cost them across a career. Scope creep, The gradual expansion of project scope without corresponding budget or schedule adjustments is one of the greatest risks you face to project success and to firm profitability. Every project starts with an agreed scope under AIAB 101, and every project drifts as owners request enhancements, programs evolve, and consultants surface requirements that were not in the original brief. The architect who manages scope actively, documenting every change and its impact on fee and schedule, keeps the project profitable. The architect who lets scope drift without documentation absorbs the cost of every drift personally, and projects that should have been profitable end up at a loss. Worse, when the owner refuses to acknowledge a verbal scope addition and the architect tries to bill for it, the dispute that follows lands the architect on the wrong side of the documentation rule, and the lawsuit that follows traces back to whether the conversation was in writing. The exam tests whether you know how to categorize a change, route it through the right process, and document it to defend the additional services request. 5 change types each have a defined architect response. Knowing which one you are looking at drives the right action. 5 change types each have a defined architect response, and the source of the change determines whether additional services apply. Owner-directed changes happen when the owner adds or modifies requirements after the original scope was set. The architect documents the change, assesses cost and schedule impact, and submits an additional services request with the requested fee. The owner has the right to direct the change. The architect has the right to be paid for the additional work. Code-driven changes happen when a code official requires a modification. These are implemented as basic services if the requirement falls within the original scope, because the architect was already responsible for code compliance. Coordination-driven changes happen when a consultant identifies a conflict that requires architectural rework. These are resolved within the design team with no additional fee, because consultant coordination is basic services under B101. Market-driven changes happen when the cost estimate exceeds the budget, triggering a VE process. And the unpleasant rule under B101 is that redesign required because the architect failed to design within budget may be at the architect's cost, not the owner's. Scope creep is the gradual accumulation of small additions that individually look harmless. The architect tracks each one, documents the cumulative impact, and requests additional services when the total reaches a threshold worth invoicing. 6 risk management practices anchor every design phase. Each one is a defensive tool the lawsuit hopes you forgot. 6 risk management practices anchor every design phase, and each one is a defensive tool the lawsuit hopes you forgot. First, maintain a design decisions log. Record who decided what and when, and keep the log in writing rather than in memory. When the owner denies approving a change 3 months later, the log is the architect's defense. Second, get written approval at each phase transition, SD to DD, DD to CD, because a phase transition signed off in writing fixes the scope as it stood at that moment, and any subsequent change is a documented change rather than a contested one. Third, use a formal change management process even during design phases, not just during construction. The design phase is where most scope creep happens, and a formal process forces documentation. Fourth, track consultant hours against fee at every milestone. When the consultant is over budget on a phase, the architect knows scope creep is happening before it becomes a financial crisis. Fifth, include additional services provisions in every subconsultant agreement. Because if the subconsultant is doing extra work and cannot bill for it, the architect ends up absorbing the cost. Sixth, review insurance coverage annually and make sure it matches the current project risk profile. Coverage that was right for last year's small project will not defend this year's large lawsuit. One rule sits above all 6 practices. Documentation is the architect's single defense when the owner denies a verbal agreement. One rule sits above all 6 risk management practices, and the exam tests it directly. The single most important risk management tool is documentation. Verbal approval from the owner is no approval at all, because owners routinely deny conversations they once agreed to when the bill arrives. The architect who documented the conversation in writing is protected when the dispute reaches court, and the documentation is admissible evidence under most jurisdictions. The architect who relied on verbal approval is personally liable for the work performed without written authorization, and the lawsuit that follows traces back to whether the architect had paper to back up the claim. An email confirming a phone conversation is the minimum documentation standard. Send the email within 24 hours of the conversation, summarize what was decided, and ask the owner to confirm or correct. If the owner does not respond, that is also documented, and the silence becomes part of the record. Scope creep without documentation is fee absorption. And a firm that absorbs enough scope creep across enough projects ends up bankrupt because the labor cost ate the profit margin. The exam asks the same question over and over. What protects the architect when the owner disputes the change? And the answer is always documentation in writing. 5 takeaways close the design change and scope creep framework, and the module. 5 takeaways close the design change and scope creep framework. 5 change types each have a defined architect response. Owner-directed warrants additional services. Code-driven is basic services if within scope. Coordination-driven is no additional fee normally. Market-driven may fall on the architect under B101 if the budget was missed, and scope creep gets tracked and bundled into an additional services request when cumulative. Owner-directed changes warrant additional services. Coordination changes generally do not. Knowing the difference protects the firm's profitability. Market-driven redesign may fall on the architect under AIA B101 if the design exceeded budget, which is the unpleasant rule that makes accurate cost estimating during design a defensive practice rather than a courtesy. 6 risk management practices anchor every project. Design decisions log, written phase sign-offs, formal change management, consultant hour tracking, additional services provisions in sub-consultant agreements, and annual insurance review. And finally, documentation is the single most important risk management tool. Verbal approval is no approval. The architect who put the conversation in writing is protected, and the architect who relied on verbal handshake is personally liable when the owner denies the agreement at deposition. You are not just running a design phase at the advanced level. You are building a record that has to hold up years later, sometimes in a deposition. Every advanced tool in this module exists for that reason. Cost analytics convert gut feel comparisons into life cycle evidence the owner can audit. Function analysis through FAST diagrams surfaces where value lives before value engineering can strip it. Systems integration converts a stack of discipline-level deliverables into a coordinated single document set. Performance specifications allocate risk deliberately rather than by default. And peer review converts a single-author design into a multi-author validated design before construction documents lock in coordination errors. Every advanced lever you reach for is producing the record, and that record is what protects the project, the practice, and your standard of care if a claim ever arrives. Cost analytics is the first cluster because lifecycle math and reconciliation are the tools that turn cost from anxiety into auditable evidence. 3 tools turn cost from gut feel into evidence. Lifecycle cost analysis under ASTME 15-57 frames the question across the analysis period rather than just at the construction handover. First cost, operating cost, maintenance, replacement, and any salvage value all roll into a present value comparison that lets the architect recommend a higher first cost system because the life cycle math favors it. Total cost of ownership is the broader frame the owner actually tracks. It includes the soft costs and operating burden the owner carries over decades, and the architect's discipline is to align design recommendations with that broader frame rather than just construction cost alone. And reconciliation is the rhythm that keeps cost honest at each phase. The estimator updates the projected number against the budget, Gaps surface as design choices the team can address with intention, and the project avoids the bid day surprise that derails programs and schedules. Function analysis and systems integration form the second cluster, the disciplines that protect intent and coordinate output across the design team. 3 disciplines run in parallel through DD and into the CD phase. FAST diagrams, function analysis system technique, map the building's program needs to cost, surfacing where value lives before value engineering can start cutting blindly, so the team can answer the question of which functions the budget cuts can come from without erasing what the project actually needs to deliver. VE, by delivery method, recognizes that the timing and authority of value engineering is different across procurement models. Design Bid Build forces VE into a bid day rescue because the contractor enters the project after the design is complete, while Design Build and CMAR fold VE into the design phase because the contractor sits at the table from the start. And systems integration is the discipline that has to happen during DD. Structure, MEP, envelope, vertical transportation, and fire protection all reconcile their requirements into a single coordinated document, and the architect runs that coordination as the team's central conductor. Specifications and peer review close the arc, the documents and external checks that make the design phase defensible long after construction is done. 3 levers close the arc and lock in defensibility. Performance specifications state the outcome the contractor must deliver: air leakage rates, acoustic ratings, structural deflection limits, and let the contractor select the means and methods to achieve them, which shifts selection risk away from the architect and onto the contractor, while preserving the performance the design depends on. Substitution procedures live inside the project manual under CSI Section 16000. The spec governs which substitutions can be considered, what supporting documentation the contractor must submit, who reviews the request, and how the risk shifts when the architect accepts a substitution after award. And peer review is the external check that catches the errors a single design team cannot see. Structural peer review on tall and irregular buildings, code peer review on complex occupancies, and discipline-level cross-checks before construction documents. And the peer review record becomes part of the standard of care defense if a claim ever arises later. 4 takeaways close the advanced arc into the evidentiary discipline that distinguishes a senior licensed architect from a junior one. Take away from the advanced arc the evidentiary discipline that distinguishes a senior licensed architect from a junior one. The lifecycle reframe under ASTME 15-57 takes the cost question out of first cost only territory and reframes it across the analysis period, which is the only frame that earns a higher first cost recommendation on an LED, an envelope upgrade, or a high-efficiency mechanical system. Reconciliation as cadence keeps cost honest at every phase. The estimate aligns with the budget, gaps surface as choices the team can address with intention, and the project avoids the bid day shock that derails programs and schedules. FAST plus integration discipline surfaces where value lives before value engineering starts cutting, and systems integration during DD resolves coordination conflicts before they print into construction documents and trigger RFIs in the field. And the documentation plus review pair locks defensibility. Performance specifications allocate risk deliberately. Substitution procedures govern post-award changes, and peer review across structure, code, and discipline-level coordination becomes part of the standard of care record if a claim ever arises. The advanced phase produces a project record you can defend years later. That is the standard the module is training you to.